Don't know if there's volume with it or not. Anyway. While I dry out here, let's have this online. So this is a historic dam collapse in 1959, long before you were born, not before I was born. I think I'd have been one. And it was an arch dam that was made to supply water in the south of France. Location is very close to Nice. And the design of this is a bit like now Hoover Dam, right? So it certainly wasn't the first arch dam. Hoover Dam was a civilian conservation corps type recovery project in the 1930s, and this is much later than this. But it was an interesting dam because it was the first of a series of dam disasters in the late 1950s, early 1960s. Actually not so much caused by structural failure of the dam itself, and you can see in this, it's kind of a thin-skinned arch dam that has not much volume to it and not much mass to it, but relies on kind of its structural integrity to push back against the water which is impounded behind it. And in this particular case, the abutments, the rock on the side, had faults in it and moved, and as a result was ruptured. And of course the problem with all ruptured dams is that you have a big impoundment of water which all of a sudden is released, and if there are people living downstream, then that's obviously a problem. This killed 400 and some people, I think, in time. There was another dam that failed in the Italian Alps not much after this, in the early 60s, the Veillon Dam, which was a different failure where a landslide into the dam, into the impounded dam, actually evacuated all the water from the impoundment, the reservoir, over the top of the dam and downstream, and killed even more people, I think, down in these constricted valleys in the Alps. So this was a wake-up call. I think the guys who designed this, one of them committed suicide afterwards for this particular dam. And so something that relates to this class, obviously, because of what we're talking about in terms of fluid pressures. Clearly it's the pressure at the back of the dam that is forcing it to move, or trying to make it move. It's being resisted by the abutments. If the abutments aren't stable, then they move. So that's what we'll talk about next week, forces on structures. But it follows on directly, of course, from what we've been talking this week about pressures at a point, which of course rely on the fluid above it to be able to figure out exactly what the pressure at that location is. So that's one exposition of this. The other one, I guess...
To suspend drill, perform the following 6 functions. To stabilize the wellbore while controlling subsurface pressure. To suspend drilled particles and transport them to the surface. To cool and lubricate the bit and drill string. To assist in formation evaluation while minimizing formation damage. To assist in supporting the suspended drill string, and to transmit hydraulic horsepower to the bit. Let's look at each of these functions individually. The normal fluid pressure gradient of the Earth is about 0.465 psi.
So this is perhaps a bit more topical, maybe to some of you. Certainly some of you will get involved in drilling, petroleum engineers, environmental systems engineers. Typically, the wellbore is filled with water. Typically that water is a drilling mud, which is water plus some fluid, or some solid rather, to make it a slurry, which is heavier, denser than water. And so the idea is that if it's denser than water, then the column of that fluid will exert a larger force going into the formation than the water that's present in the formation, which could also be hydrostatic, or more than hydrostatic. And of course, if you put more weight in the drilling mud, you can also counteract the actual stress that's in the rock. You do the same calculation. The unit weight of rock is 2,500 kilograms per cubic meter versus 1,000 for water. And so sometimes in places like the Gulf of Mexico, where you have very unconsolidated reservoirs, basically sands, they'll flow into the hole if you don't have something to keep them back out. So drilling muds are used to do that. They also have these other functions that mentioned there, not least of which is to be able to recover the cuttings from the base of the hole where they're being ground. This is drilling mud here. We talked about materials which are thixotropic, that if you leave them to stand, they become kind of semi-solids and they have some shear strength. And that's basically the behaviors of drilling muds. And so they're also, when you drill, you pump the water down the center of the drill string to the bit. The bit is cutting the rock, and then it recirculates the cuttings along the outside of the drill string on the inside of the hole up to the surface where you can look and see what you're drilling through, but also get that stuff out of the hole. So some evidence maybe in terms of the things that we might, the reasons that we might be interested in understanding measurements of fluid pressures at a point. I will turn off the podium light because I don't need it. So today, as I mentioned, we're going to talk about some examples. I guess there are just a few things that I thought would be useful to look at. It's a shame that we have to talk about this. We don't have to, but I think if you looked at the Penn State, you must all get the Penn State daily email, right? I'm not sure what it's called. But there was an article in there and a little 5-minute video which is worthwhile watching, I think. But obviously, in the current climate, it's something that certainly we can't ignore. I'm not your flight attendant, so you don't need to wait for me to tell you to do anything. But the basic ideas of this are quite simple and quite straightforward. And that is, if there is some kind of problem, get the hell out of here. That's basically the deal, right? So in this order, decide to go if you can. If for some reason you can't, your way's blocked, hide maybe. And if it's beyond all hope, then you have to actually fight. There's 2 exits. I don't think there's an exit to the back, right? It's kind of curious, because if you look at the back of the building, outside, there's a series of steps that go down and into it. But maybe it goes in underneath this auditorium. But anyway. So the good thing is there are 2 good exits on either side, so it's tough to block. I guess if you're trying to hide or block entry to someone coming in, it makes it more difficult. So I guess it cuts both ways. But anyway. So be in the same way that you should take charge of your own education, I think you should think about taking charge of your own safety should it come to that. Let's hope it never does. In terms of where we are in this class, we're in 10 Sparks, of course. Just to make some comments of where we are. We're at the end of the second week. Next week is Labor Day, but the other 2 classes are online. You're welcome to come here and use this room, of course. This room will be open. You're welcome to come on Monday as well if you so wish. If you want to come here and have it turned on so you can pretend you're in the theater having a beer and a burger while you look at some entertainment, then you're welcome to do that, I think, or to do whatever you want. But the material this coming week is online with these optional extra credit quizzes. The lines that are across here are for where the material ends for each of the tests. So the first midterm is on the first 3 weeks, actually plus 4.1. 4.1 is accelerating fluids. So we talk first about fluid statics, weeks 1 through 3. We talk about Bernoulli's equation for moving fluids starting in week 4. But the first one is to do pressures in an accelerating can of Coke or a glass of water. And so it fits more logically in fluid statics because it is fluid statics. And so the material, basically, each of these lines here denote the material, the blocks of material. So 1, 2, 3, and the logical breaks in this for each of these. And so what we'll do is this will be something posted online. I'd imagine it'll be posted online before that. You can look at the previous crib preparatory videos for the review sessions, I guess. And so they include some information about what the questions specifically are on, not the questions themselves, and also some discussion of the material you need to be able to do it. So there's just a basic recap, right? So that's kind of where we are. So next week is online, as you see from this. Okay? Any questions as we're kind of going easy today? All right. All right. So, let's get rolling. Bless you. So, today, as I mentioned on Wednesday, I thought we would go through some basically mainly examples. And so I'm going to stick with my script on this today. So just to recap, the things that we've talked about so far, we've maybe done it to death, but we know that fluid pressures at a point act the same in all directions. We know that if we take away accelerations from our system, then as we move horizontally, pressures don't change, but as we move vertically, this expression is always true, with this being equal to density times gravity, density of the fluid, which gives us this linear distribution, piecewise linear distribution of fluid pressure at a point. If the fluid doesn't compress, in other words, density is constant, as in a liquid, then we can always get the fluid pressure at a point by knowing it somewhere and adding on an increment due to a change in elevation. And we'll talk about what those changes in elevations are. This is always plus or minus, depending on when we're going up or down. So we can always use this in an incompressible fluid. And if it's a compressible fluid, we can't assume that this is the case. We have to assume that density is not constant. And if we do that, then we end up with some different expressions, which we won't revisit here, but we talked about them for moving up and down in the atmosphere, where the pressure distribution with elevation is not linear, but curves. We finished off last time the fact that we'd like to use manometry to be able to measure pressures. And when we talk about fluid statics next week, we'll be interested not in being able to just determine fluid pressures at a point, which is what we'll do today, but being able to look at the distribution, like this triangular distribution in the drilling mud we just saw, and being able to integrate that to figure out, for instance, what the force is on the back of the Malpassé Dam, so we can equate that with the resistance that comes from the concrete, which is trying to shear through. And so that's our interest in being able to take this the next step to look at forces on structures due to fluid pressures. But for today we'll just concern ourselves with fluid pressures at a point. We know that if you look at pressures with depth, we have a convention where this is negative. We know that if we choose a particular location where we know the pressure, which is P0, then we can always get the change in pressure, which is just, if you like, it's just this is delta Z, and this is delta P. And delta Z is just what we're going to call H. And so this value is either positive or negative. So when we look at the manometer rules, if we go up in the column, then the pressure diminishes. So if we go up, the pressure reduces. So we have to use a negative distance to connote that. And if we go down, it's positive. If we go horizontally in a fluid, this is just our indication that as we go horizontally, the pressure doesn't change. If, as in the barometer, there's an airspace which is evacuated, then that airspace has to be filled with vapor from the fluid which is underneath it. In the case of the barometer, it's mercury vapor. And so if it's evacuated, then the pressure within that airspace, or that vapor space, has to be the vapor pressure of that liquid, mercury in that particular case. And we made the case that if we go up and down in a gas, if there are liquids in the system, then because the density of a gas is of the order of 10 to the minus 3 of the density of a liquid, then often we can neglect the unit weight. So in other words, we don't have to, and I guess if you like on this, what that would look like is if this is a liquid, then this would be a gas. You go down a long way, there's virtually no change in pressure. And that's the rationale for that. Okay? So those are the tenets that we will work on. And so we'll just work through some examples. I'll try and do it. I'm not sure I need to calculate every single term in it, but you just get into the gist of how to solve these systems. So those are the manometer rules that we'll use. I should reinforce the idea that everything in your tests will be in SI units, period. And so these are not, as you see, but they're just convenient ones to use. So what's the question here? We have a tank that's inverted. It's got a tube coming out of it. That tube has a manometer fluid in it. The tank, I think, starts off, you put it in with an open tube, you get the manometer fluid in there somehow, and at that stage, the water level in the tank would be the same as outside, and you pull the tank up. You can imagine if you pull a tank up, then you're exerting some kind of, it's like opening a bicycle pump, right? You have a suction inside that develops. And so you can imagine that if you're sucking up the water, then this is probably less than atmospheric at this point here. And so from what we know about manometers, if we think of this being the gauge fluid, this suggests that the actual pressure within the tank is actually overpressured because it's pushing this up, that the pressure here is larger. Actually, the pressure is equal to this height of mercury, whatever the gauge fluid is. So this perhaps is wrong in terms of how it's set up, but it doesn't mean that we can't solve it the same way. What do we know about the boundary conditions? We know that the pressure here is atmospheric. We know that the pressure here is atmospheric. And so we could use those to be able to work our way through the system. We know that because this, we can get from this point to this point here, that this point also would be atmospheric. And I guess the question is, what is the value of H that we think is in here? I think H is going to be less than this height here, as it turns out, just from what we've just said. But the solution to this is pretty straightforward. We start off at some point where we know the pressure, and we work our way to a point where we don't know the pressure. It turns out that the points we have in this system, we both know the pressure. So if we start here, which is this, so this, if we take gauge pressure as 0, then these are both 0. Actually, this is as well. But if we start at PB, we go up to here. We're going up, so we're reducing pressure, manometer rules. So it's going to be 2 feet times the unit weight of water. We end up at this place. We're in air. The density of air is approximately equal to 1 over 10 to the 3 times the density of water. So we probably don't have to worry about it. So we can go from this point directly to this point and have the same pressure. And then we can go down across to this point here, and that will have the same pressure. And so the same pressure, PA, would be at this point as well. And then from this, we go up an amount which is going to be equal to H minus 3 feet. So it's going to be minus H minus 3 feet times the unit weight of the gauge fluid, whatever that is. And that's equal to PB. We know each of these are 0. And we also know that, I'm not sure we've talked about it much in this class, that the specific gravity of this fluid here, the gauge fluid, is equal to 2.5 times the density of water. So rho gauge is equal to 2.5 times rho W. So in other words, unit weight gauge is equal to 2.5 rho W. And so we should be able to rearrange this. So this is equal to 0 on the left side. And so I suppose this is what we want to know. So we could rewrite this as, just to get that on this side, this is going to be equal to plus h times gamma g. And this is going to be equal to minus 2 feet plus 3 feet times gamma g. And I guess, yeah. And is that everything we have? Yeah, it is. I suppose we might make the substitution that gamma, this is equal to 2.5 times gamma water. And this is also 2.5 times unit weight of water. And if I move it up so I can actually use my pad a bit better and rearrange this, then we're going to have 3 times 2.5 minus 2, all multiplied through by the unit weight of water, right, which is here and here. And that's going to be divided through by, that's going to be equal to h, and we're going to divide by 2.5 times the unit weight of water. And that is going to be equal to what? 3 times 2.5, we can get rid of these, right, because we don't need them. 3 times 2.5 is 7.5, minus 2 is 5.5, divided by 2.5, I think it comes out to 2.2. And so 2.2 means that actually the height of the gauge fluid would actually be here, which is what we said before. So the difference between these, this would be delta H that is present in the system. And that kind of makes sense because we think that there's a suction in here. If there's an overpressure in here, then this level in the tube would be higher on the outside. If there's an underpressure relative to atmospheric, it would be the opposite. So it makes sense. Not asked in this question, but you have to apply a force to move this up here. And so I guess you could do that in a couple of different ways. If you wanted to calculate what is R, does it get done at the bottom? I guess I do it at the bottom. 2 ways to do it, right? In the same way that we did a capillary tube, since we know that the fluid pressure along this boundary here is equal to atmospheric, which is 0, then we could just cut this off, and in other words, the weight of this here has to equal R. And of course the weight would be equal to what? 2 feet times unit weight of water times area. And so if we knew exactly what that was, we could do that calculation. I suppose the other way we could do it is that we could also equate R, and we haven't started talking yet about pressures on structures. Clearly there's going to be a pressure in here which we haven't actually calculated, but we could calculate because we know this pressure. Well, what is PA going to be in this? It's going to be equal to, if I can draw this, yeah, let me draw it. It's perhaps a useful diagram. If we drew the pressure, I know I'm kind of overprinting everything here, but you'll see the point soon enough. This pressure here has to be 0. And so if we thought about the magnitude of the pressure, then right at this elevation here, if this is the pressure distribution in water, then this by definition would be equal to P B, which is atmospheric. If we go up this amount here, didn't quite draw it right, then the pressure at this point is going to be equal to this negative amount, a tension. So we can calculate the magnitude of PA, which is just going to be this. And PA is going to be acting, pulling down on this. This is going to be 0, so this is going to be a negative pressure, right? This delta P is negative. So this here is PA. And this has to equal PA multiplied by area is equal to... We're not talking about pressures on structures yet, but we could do it in two ways. Often you can find you can do these in a couple of different ways. Okay? So this is probably more advanced than we need because we'll do that next week. But the bottom line is that we can just work our way through a system. If we know the pressure at a point, we can rationalize our way through the system. That's how manometry works. Okay? Yeah.
So why do you assume that the pressure at point B equals to 0? I mean, there's the atmospheric pressure
at this B here, or this B here, or this B?
that one.
Top one. This one? Because it's atmospheric. So I guess it also relates to this, right? As we go up from this point here, clearly we go up through H feet of air. And so the pressure here is going to be slightly larger than this. But the change is going to be so trivial compared to the changes in the liquids, we don't care. So it's basically this rule here.
So there is a pressure at point B, but we are ignoring that.
We could account for it if you wanted to, but it would make it would make a fraction of a change to our final answer. Yeah, it's just a convenience that we ignore it. Good question. Okay. All right. So I'm not going to dwell on this. No, let's come back to that if we have time. We can better spend our time doing other things. Okay. Ready for another one? Same idea. So read the question. A mercury manometer is used to measure the pressure difference in two pipelines, pipeline A and pipeline B, going into the board. Fuel oil flows in one of them. This is this one. And it has a specific weight of this amount. This is our unit weight. There's an air pocket that is here that gives this elevation and this elevation as the same. I guess you need to know that. If you imagine a bubble rising in something, it'll rise in a tube and it will take up the same, just the same as if you have a piece of Tygon tubing with water levels in it, and the big bubble is the external atmosphere. The water will have the same elevation on both sides, because the pressure here in both sides is the same, just like it is an atmospheric pressure on the two ends of the Tygon tubing to be able to transfer your level elevation here to here. And we need to know, if we know the pressure here is equal to 15.3 psi, even though we're not working in English units, imperial units, then the question is, what is PB? So PB is the one we don't know here. Remember the other one was open-ended and we did know at both ends. So what we do is we work from this. And I'm just going to echo what's going to be written underneath here, is that we start off at PA. That's this point here and this elevation here. We need to get down to the gauge fluid. The gauge fluid starts off here and here, if you can't see it because of this. And so we need to go down in the fuel oil by 3 inches plus 18 inches. So we're going down, so we're adding. So this is 3 plus 18 inches. If our units are in pounds per cubic feet, etc., then we divide by 12, just to do this. This is in inches, and this is 12 inches per foot, I guess, if you want it. And this is multiplied by the unit weight of, I'm going to call it fluid A. just because it's today. Now we're in the mercury. We need to go down to this point now here, which is going to be plus 6 inches. I guess 6 over 12 again, multiplied by the unit weight of mercury, the gauge fluid, Hg, this term here. We find ourselves at this point here. We work our way up to here to get to this point here. We're going up, so we are subtracting. Minus 6 inches plus 18 inches. Again, divided by 12 for the same reasons as before. And we're in a different fluid, charcoal B. We're in a gas for the same reason we talked about the air bubble being the same elevation. To be able to get to this point here, then we can go directly to this point here. That's the same pressure. And now we want to be able to get from this pressure to point B. This is going to be 5 inches total, minus 3 inches. We're going down, and so we add 5 inches minus 3 inches, again divided by 12. I'm running out of space. Multiplied by the unit weight of fluid B. And I'll write it over here. And this has to be equal to the pressure at point B. That's it. And I think it's exactly the same expression. I'm not going to go through the calculations, but what we want to know is this. And we pretty much have everything else. We know that this is 15.3 psi. We know all these lengths. We know the unit weights of each of the fluid, specific weights of 53 and 57 pounds per cubic feet. So we know this. We know that. I guess you need to know that mercury is some magnitude. Is it given here? I don't see it. You need to know that mercury is something like 13,000 kilograms. Doesn't help you here, right? Kilograms per meter cubed, whatever that is in English units or imperial units, whatever you call them. And then you can work out the magnitude for this one remaining component, right? Just have to work your way across the system. Right? Another question. So what is the, so the idea is you have a form which has an open top that you can pour concrete into, and that once you poured concrete into it, to stop the form lifting, you have to put a weight on it to be able to hold it down. And that weight is predicated by the idea that the concrete in the form is going to try and dislodge itself to be able to push the form up and to flow underneath it. And so the question is, how big how heavy does this bag of sand have to be able to take care of that? And so I guess the key thing here is to realize that you can do a free body diagram. And the free body diagram, one of the free body diagrams that you can take would be to basically isolate this whole form by going around it. And actually that's the one that's written here, including going across the bottom. And so you've isolated this completely, including the fluid pressure that's acting on the base of this, of the concrete that's in here. And what you can do is then you can resolve forces in some direction. They've called it Y, we'd probably call it Z. And that is the components going down are going to be the weight of the sand, the weight of the concrete that's inside the form, and the weight of the form itself, which has a finite weight. And acting up against this, there's going to be a fluid pressure multiplied by the area of this base. So these are the three components acting downwards. This is the component acting upwards, different sign. And they have to sum to 0 because this is just F equals ma. and the acceleration is 0, so this is equal to 0. There are 3 components. We're only interested in the direction of the y. Right? And so that's basically what the calculations are. I suppose just to illuminate it a bit more, it might be worthwhile suggesting that this is going to be what the pressure distribution looks like due to the concrete. So that if we look at the base here, then the magnitude of the pressure at point B is going to be this. This is going to be, I guess in what we've done before, this is 1, right? And this is the unit weight of the concrete. This is just the depth change. So at this height, we know what are the components here. The risers are 18 inches high. So the total height of this is 8 plus 8 plus 8, which is 24. So this is 24 inches, I suppose, if we want to, divided by 12 times the unit weight of concrete is equal to P. So this is just a graphical indication of that. The reason for drawing this out, which is useful, is also to be able to make the point that we need to be able to, actually for this calculation we don't need to do it, but I guess what we don't want to do is to assume that the pressure acting underneath this step here is isolated and is equal just to the height of this, the pressure due to this. Because the pressure acting on this step, right at this point, is equal to this pressure plus this weight. And so everywhere along this base, the pressure is uniform. And it's given by the maximum height. Just as if you have I guess this perhaps seems a bit more strange with concrete, but if it's filled with water, that's exactly what it would be, right? If you went down to the bottom of the swimming pool in water, you'd feel the weight above you. If you went over here in the same swimming pool, you're still feeling this height of weight above you, weight of water above you. And so we need to be mindful of that. And so if we do that, then we can just calculate what the components are for this free body diagram. And so this is what we'd like to know, right? We'd like to know what the weight of the step is. And we want to define that in terms of the weight of concrete, the weight of the form, which we're given. This is 85 pounds. We've already said that the pressure at B is going to be 24 inches over 12 inches multiplied by the unit weight of concrete. The area are that these are each 10-inch treads. So this length here, I guess, is 30 inches. And this length here, I think for the whole step, you can see at the top is 3 feet. I guess we could do it at 36 inches, whatever. And so this area here is just going to be 3 feet times 2.5 feet, if we're doing it in feet. So we know that. The weight of the concrete is going to be what? It's going to be this volume here plus this volume here plus this volume here. And so what is that? The weight of concrete is going to be equal to the unit weight of concrete multiplied by 3 feet, which is this length here, multiplied by, this is 10 inches, right? And this is 8 over 12. So it's going to be 10 over 12 times 8 over 12, which is the first one. Plus 10 over 12 times 16 over 12, I guess. Plus the same. I guess I could have kept 10 over 12 outside, right? Times 24 over 12. I'm sure you could probably do that faster than I can. And so now we have the weight of the concrete. And so if we know weight of concrete, weight of the form, and the pressure that's acting, then we can also the final remaining component is the weight of the step. And so those are just the calculations that are given here, and it turns out to be this amount. So like all of these questions, it's just a matter of figuring out exactly how to be able to do it. The other way to do it, of course, is to actually just use the pressures, right? You should be able to get the same result. Just like we did the suction of the cylinder in two different ways. I guess, am I able to do this here? I'll try to do this. The other way you could do it is you could also draw a free body diagram that was slightly different. And so the other free body diagram you could draw could be this one. It's a bit of a tortuous one to draw. But if you draw a free body diagram like that, then the only thing that you have to account for is that you have, and I'm going to get rid of that. Remember that that is there, but let me just get rid of it. So if you do that, then you realize that all you have to account for is the fact that there's a fluid pressure acting here on step 1. There's a fluid pressure which will be smaller acting here on step 2. And there'll be a zero fluid pressure acting on the open component up here. And so in this case, if you wanted to be able to do the free body diagram, then we're going to have to account for the weight of the sack of sand plus the weight of the form, which is this whole thing that's pulling down. There is no weight of concrete because now the concrete's excluded, minus the pressure at point of step 1 multiplied by the area of step 1 minus the pressure at point step 2 multiplied by the area of step 2, and that's equal to 0. And so now the weight of the form is the same as it was before, so we have this. We know that the areas of the steps are just the areas of the treads, right? So A1 is equal to A2, which is equal to 3 feet multiplied by 10 inches. So this is the area of the step. And we know that the magnitudes of the fluid pressures at these points are given by these amounts here. So P2 is going to be equal to the unit weight of concrete multiplied by 8 inches over 12. And we know that P1 is going to be equal to the unit weight of concrete multiplied by 16 over 12. And you should come up with exactly the same answer, just because it's the same question. Okay? Tired or stunned or ready for a vacation? Very quiet, very quiet. All right. So lots of different ways to solve problems. I'm not going to go through this one either, other than to note, it came up to the question now, why, in gases, we typically assume, gases in some respects are more complicated. You remember that when we calculated the pressure distribution in the atmosphere, no longer was it uniform, but as we went above if we looked at the fluid pressure within water, and if we looked at fluid pressure as we went in the gas, it would asymptote to some magnitude. And that asymptotic magnitude would be 0 pressure absolute, and this amount here would be equal to our 101 kPa. And so this actually is really exaggerated. This is almost, you'd be able to barely see this relative to this axis if this was in the same scale, because this is 1,000 times more dense than the gas. We always assumed that because a gas is quite compressible, and we get that from the ideal gas law, right? We know that this is equal to the compressibility of gas. So the density of gas is equal to P over RT times the molar weight. Because density changes with elevation, with pressure, then we have to account for that. Because we've said that liquids are functionally incompressible, then we could ignore the fact that, and we can make density constant. It clearly isn't constant because we know that from the compressibility of, or the modulus of a fluid, a liquid, it has some finite compressibility, because when we squeeze water, it changes volume as we put a big pressure on it, but just not very much. And this is an interesting example. Never ask you to repeat this, but it does the calculation if you assume that the water is slightly compressible versus the assumption that it's a constant density. And if it's slightly compressible, as the fluid pressures increase at depth, then it becomes denser. So you'd expect, if you account for compressibility, as you go to deep depths at the bottom of the ocean, the true pressure would be slightly bigger than the one that we'd calculate based on assuming that density is constant. But you see that the difference is negligible. It is maybe, could be 2%, right? It's a little more than 1%, maybe and less than 2%.